Hi there, this is Jacob Nash, and in this video we'll be looking at how to find work with integrals. So first of all, what is work? You've never taken a physics class, you might not know what it is. So in case you don't know, if you apply a force on something and it goes a distance, work is done. So basically that explains why the equation for work is just force times distance, because if either of them are zero, then there is no work. So that's why there has to be a force and it has to go distance. But the units can be two different things. I'll start out with saying that it can be joules, which is way more common, or feet pounds. What's the difference? Gravity is the difference. So, and pretty much the system of units is different. So, uh, joules, that unit can also be written as Nm. You don't really have to know that, which means Newton meters. But if you see the unit newtons times meters, that's joules, and the unit of force can be newtons, and the unit of distance can be meters. If that's the case, um, then that's where you'll use joules as the unit for work. And that would also mean like newtons, force equals mass times acceleration, right? So newtons already includes acceleration because gravity is the acceleration in that case. So this, I don't know, it's possible that some people might have not learned it, so I'll just write it out. I mean, in case you don't know, force equals mass times acceleration. Acceleration can be equivalent to gravity, which is uh 10 meters per second squared, more precisely 9.81. We'll just say 9.8 meters per second squared. Um, so that's basically really work is equal to mass times acceleration times distance because force equals ma. So um, that's where you would use joules. Feet pounds is if you see those units. If I see feet or pounds, uh, weight, if you see something that's already in pounds, pounds already includes gravity and that calculation. That's the difference. What's the difference between mass and weight? Well, this is equivalent to the force is also equivalent to weight. I'll just write WE because um, mass and weight are not the same thing. If you have weight, then you've already factored in acceleration or gravity, basically. So all that to just say that you could see either of those units. You don't have to know those specifics that I just said. I just said that to explain why. But if you if you see stuff like meters, then you'll know to use joules, and if you see feet or pounds, use feet pounds. Um, that's just an example of work. That's pretty easy, right? Mass times acceleration times distance. Um, okay. So if we want to find um, the work done on this graph, we can't just use that equation because it changes. As you can see, the force right here, it goes down, it goes back up. So we can't just, technically we could do area under the curve here and area under the curve here. That would work by our shapes that we see, but we can also just do integrals. But we will have to do three separate ones. And this is kind of a stupid question. Well, not stupid, but you have to, the equation changes multiple times. That's not even the easiest way to do this. The easiest way would be to do the area under the curve in terms of shapes and add them together. So I see a triangle here, I see another triangle, I see a rectangle, just like we've done before. But that's just to show you that you can use an integral, but disregard that example because we're going to look at better examples. Um, for example, spring. Um, we're trying to find a work done by a spring. A spring is going the force for a spring is K times X. K is the spring constant. It will always be given to you. Well, actually, it might not be. You might have to solve for it, but that's not really that hard to do. Um, so here we go. This is the function, and if you look here, uh, the spring has a natural length of 50 centimeters. A force 50 newtons will stretch the spring to a length of 60 centimeters. So the spring constant is 500. It doesn't say that there, but um, that's what it should say. They might ask you to find it by like telling you something else, but that's only if it's more complicated problem. So we're gonna say that the spring constant is 500, and it's saying that the tricky thing is that we have to be in meters. You can only ever be in meters or feet, and we're going to use meters just because I see centimeters already. That's easier. Um, and newtons. So it's saying, what's the work done stretching it 20 centimeters? Now, why is it one fifth? Basically because 20 centimeters equals 0.2 um, meters, which is I don't know why it's written in a fraction, but just 0.2. So that's why that's what the bounds are. And then it's that simple. It's just 500 times x. X is just remains the same, and you just plug in 500 for k, which is what k was. So that's as simple as it is. You just do the bounds. You might have to adjust the units like we did, and then we plug in 500 for k. Now we're trying to do it from 100 centimeters to 110. Once again, I just convert that to meters, and it would end up being 0.5 and 0.6, or 1/2 and 3/5. Um, and then you might get a question like this where it already tells you to work, and you have to find one of the bounds, like how far was it stretched? So D is what we're trying to solve for. All you do is, solve for an equation like you always would. If we do the antiderivative of this, we would get 250x squared, and then you solve for d because we know if we were trying to solve this, it would be 250d squared minus 250 0 squared, which is just nothing. So uh, we get 2 over 25 equals 250d squared, and then you just solve for d, you take the square root, and then you get what it is. So you might have to do that occasionally. I apologize right now that this video, I feel like this video, I'm kind of going fast with this. Um, please do ask questions if you have any questions. I do realize this is not a very high quality video right now. I'm just trying to move through this fast. That's kind of the purpose of these videos. They're supposed to be review, so that's why I'm going through this fast, by the way. Apologies for that. All right, let's look at one where we are looking at pulleys. Um, so a uniform cable that's 30 feet long, weighing 60 pounds, hangs vertically over a pulley system at the top of a building. Steel beam weighs 500 pounds, and we're trying to find the work uh, to pull the beam. So the first thing that you should always do is draw something. So we're saying it's a 30 feet long cable. The cable itself weighs 60 pounds, and we're trying to pull up a beam that is 500 pounds. And this is just, let's just say that's the thing the pulley's on, and we're moving this thing up, and what's the work done? So keep in mind, here's the thing, since the cable itself weighs something, we have to calculate the work for both separately and then add them together. This is cut off down here, but that's what it's supposed to say, that we add them together. So to find the work of the beam, all you have to do, the beam is going to stay the same as it goes up, right? It's just the same. It's the same thing as it goes up. So all you have to do is the one-time calculation. And what I mean by that is that you don't have to do an integral. You just do force times distance. Uh, the force is this. That goes back to what I said at the beginning of the video. Since it's in pounds, that is a force. The unit of force is either pounds or newtons. So this is the force. Then the distance is 30 feet, right? So that's the feet pounds. This is the work for that. And then the work for the cable, we have to do an integral for it because as it goes up, it does not remain constant. The the work done on the cable that will change as it goes up. So from 0 to 30 are our bounds, and it's a simple calculation. We just plug in the function um, times x, and I have the x over there to just not make you confused, like fxx. But it's just basically x times the function. And the function in this case is just going to be how many pounds per feet. So 60 pounds per 30 feet. So that really is 2 pounds per feet. So that's why it ends up being 2x. And we would just basically take, antiderivative of that and then plug in 30 and then plug in 0. And you add those two together, the blue and the red, to get your answer. So to recap on what we did, to put in simpler terms, the beam never has to have an integral for it because it stays the same. The cable always does. And you just do the function times x. And then you add those two values together. Now, you might have an example, of course, where you don't go all the way. So what if you're same question, but we're only going 10 feet? Um, we do the same thing, but instead, obviously the distance we plug in 10 instead of 30. And and the bounds here are going to be 20 to 30 instead of 0 to 30 because uh oh, well, I erased a drawing. You wouldn't do 0 to 10 um because we put 30. If the drawing that I erased, 30 is considered to be the top. So if we're saying only 10 feet, it's not going to be from the bottom to only 10 feet up. It's going to be 10 feet to the top, 10, 10 feet away from the top to the top. So that's why it's always 20 to 30. It's this top thing is always going to be total length. So that's why it stays as 30. And then we make it 20 on the bottom to make this whole thing 10. So we do same thing as before. That's the only thing that changes. So that's it for this video. This is really not as common of a topic that you'd see, but I just wanted to have a review on that. Like I said, my videos are typically a little bit higher quality than that, but I was trying to go through it quick, and not trying to take too long on like, the basics of like what work is, assuming that most people already have had a physics class or something like that. So thank you for watching.